Sasha, welcome and thank you so much for being here today.
Thank you very much. Good morning, Kate. And I appreciate very much the opportunity to talk about our products, our optical DSP related oscillators as part of a webinar which is attached to the virtual show sponsored by All About Circuits, and we are very thankful for the opportunity to do that.
Well, the pleasure is all ours. Thank you. Let me just start here real quick. Not everyone in the audience obviously is going to be as familiar with Raltron. So could you actually, before we get into all of the nitty-gritty goodness of oscillators, could you tell us about Raltron, who you guys are, and what you offer?
Okay, thank you. Raltron is a frequency components manufacturer. Frequency components are crystals and a variety of crystal-based oscillators of various classes of precision. Our company is based in Miami, Florida. We have operations in Florida, also a number of production facilities in Asia. The company has been in business since 1983. We are still privately held today. The types of products that we are involved with are, besides crystal resonators and clock oscillators, precision oscillators, things like VCXO, TCXO, and OCXOs, microwave components, VCOs and PLLs, some board-level products for clock synchronization and time synchronization, particularly for telecom infrastructure. And more recently, we have entered the components for wireless applications for IoT, things like filters, SAW filters, ceramic filters, balloons, diplexers, as well as antennas and RF cable assemblies. We do our business globally. We're selling through a network of reps and distributors in the Americas and Europe and the Middle East. And we have direct sales offices and technical support offices throughout the most important points in Asia: China, Hong Kong, Singapore, Taiwan, and India. To be more precise, our product strategy is as follows. We have 4 poles in what we are doing. We offer crystal resonators and clock oscillators of all types, which are used throughout the electronic industry because all digital ICs need operate sequentially, and consequently they need precise frequency reference component, which is either a crystal resonator or a clock oscillator of some kind. So this is pretty much covering all electronic component market segments. Then we have precision oscillators, which are geared toward telecom infrastructure, broadcasting, precision instrumentation, utility metering infrastructure, etc. As I mentioned earlier, packages of components for IoT applications related to specific wireless standards, such as not only Wi-Fi, GNSS, but also Sigfox, LoRa, Zigbee, etc. And more recently, we have entered the field of oscillators for optical digital signal processor applications. So these are clock oscillators of high frequency and ultra-low jitter, and voltage-controlled oscillators with crystal, and voltage-controlled oscillators with SAW device inside. So this is pretty much our product offering. We have manufacturing facilities in Florida. We manufacture precision oscillators, VCXO, TCXO, OCXOs, and so on. And we have a couple of facilities in China and Taiwan where we manufacture the simpler products. products that encompass all these ranges.
Thank you so much for that overview. Obviously, a lot of ground to cover in general. So in this live session, obviously, we're going to focus in on that last point that you were talking about, the oscillators for optical DSP applications. So let's dig into that a little bit. Obviously, there's a increasing demand for network bandwidth. There are a lot of data-hungry devices out there, a lot going on there. And it's actually impacting the way that engineers design, right? So there are changing performance and specification requirements specifically for timing and frequency devices. So would you mind kind of approaching this from the all about circuits level is from the designer perspective, obviously. So can you talk about the challenges that designers are facing and which applications in particular might be affected?
Okay. So everybody knows that over the last 10, 15 years, and this is accelerating, there is a exponential increase in the demand of data that is transferred through the telecom networks. So this has to happen with high and faster speeds. Applications such as video on demand, movies, streaming, driverless cars that are coming fast to the market, telemedicine, all this teleconferencing that everybody's practicing today because of the COVID situation, the global COVID situation. All these things have put pressure and continue to put pressure on the telecom industry to increase the capacity and the speed of information transmission. All this coupled with 5G that you also have mentioned, the 5G telecom standard, which is being currently introduced rapidly through globally, which is designed to offer transmission rates 20-25 times higher, faster than the currently installed 4G. All these things request networks, devices, network elements that are moving the data faster through globally. This speed, this higher speed, has been only being, in particular through fiber lines, has been made possible only in the last 10, 12 years. And the industry has invented, essentially, a concept called coherent optical transmission, which was a big improvement, a big departure from the way information was transmitted previously through fiber lines, which was a relatively simple on-off type of transmission. Coherent optical transmission uses light amplitude and phase modulation, as well as polarity changing, to increase the number of parameters that can be controlled and consequently give more options for transmitting the information. In this way, there is more information that can be transmitted through the same lines with higher speed. Coherent optical transmission is being made possible by the use of optical digital signal processors. So what is happening when you transmit more information with higher debit, with higher speed through lines, you have more noise, you have frequency that is being offset, frequency that is varying, changing. There is phase noise, so there is unwanted noise that goes through the transmission lines. And there is also optical signal dispersion. And part of this of the coherent optical transmission protocols has been the introduction of digital signal processors. So you have a transmission device, a transmission mechanism a fiber line, and at the receiving end, you have a circuitry that includes a digital signal processor, which is there to compensate for the frequency offset and phase noise, etc. Mm-hmm. And this digital signal processor, which is a digital circuit, which again is operating sequentially, in order to operate correctly, clock oscillator or some kind of an oscillator attached to it, which is giving it frequency, a high frequency signal that has primarily two main properties. One, as low jitter as possible, and this jitter, the parameter is defined by the requirements of the coherent transmission protocol, and very good and increasingly demanding frequency stability over temperature and good aging parameters, so that when these digital signal processors with adjacent clock oscillators attached to them are installed in the various applications, they can function completely at all four corners of the telecom specifications. And so as the traffic continued to increase, gradually from time to time, the semiconductor industries, in connection with the telecom standards that are being imposed, is requesting oscillators with better performance. And so depending on the application, to simplify a little bit, of course, this is subject to a much wider conversation, but to simplify here, we could separate the applications in optical transceiver, the pluggable optical transceiver, and then modules and board level products, which are larger in size. So there are certain parameters that can be adapted, must be adapted in function of the respective size of the application. These applications, so pluggable optical transceivers, of course, they are used throughout network elements at the two ends of a fiber line to connect the various network elements. But also the same concepts are used for modules and board level products that go through data center interconnect applications, metro, and long haul, like such as, for example, submarine lines and so on and so forth. So there are all kinds of segments of the telecommunication market that are impacted by these issues.
Yeah, it's interesting that you frame it that way. Even at the very early portions of your discussion here, you've been touching on, the emergence of autonomous vehicles, all of the different emerging technologies that actually end up relying on on the oscillators that you're describing here. It's much more complicated than I think it seems at first glance. So if it's all right, what I'd like to do next is sort of, I'm very excited about this part of the presentation. No spoilers, everybody else, but I love when we can have an expert like you come on and explain something like this. The types of oscillators that we can use in optical DSP applications. Anytime that we can have an expert come on and explain in terms that you're familiar with and that you're an expert in, I'm just very excited to see these types of slides coming up, and I don't want to spoil it for anybody, but this is the type of thing that you kind of want these slides to put on your cubicle wall. This is the type of recording that you want to be able to refer to again over time. So yeah, could you talk us through the different types of oscillators?
Okay, sure. So the oscillators used for this type of application for digital, in connection with optical digital signal processors are high frequency in the world of oscillators. Of course, the general world of oscillators, frequencies of oscillators generally start around 1 megahertz and they can go to a few gigahertz. crystal oscillators go from 1 megahertz to maybe 200, 250 megahertz comfortably today. Clock oscillators, and then digital VCXOs, DCXOs that can go higher in frequency, up to 1 gig and gigahertz and more. For the frequencies that we're talking about here in this particular type of application are above 100 megahertz. And these in the oscillator world, the crystal oscillator world, are considered already high frequencies. So for high frequencies, the type of output for these oscillators is differential logic type. So there are two primary types of oscillators used. Lbp Packer, so low voltage positive emitter coupled logic, and LVDS, low voltage differential signaling. So these are the two main technologies that are used for the oscillators that we're talking about here. And each of them has its advantages and its shortcomings. So as I said, there are several parameters involved that need to be addressed. Lbp Packer is superior when it comes to jitter. The way the protocol is designed, the voltage swings at the oscillator output are relatively large, and because of the larger voltage swing, you have better jitter performance, of course. However, the power efficiency is less because in order to generate the wider voltage swing, you need more power to do that. And because of that also, Lbp Packer oscillators are available at, let's say today, the modern type of oscillator is powered with power supply voltages from 2.5 to 3.3 volts. There are today, the market is also requesting power supply voltages of 1.8 volts because the industry is trying to reduce the power, and that's a constant preoccupation. But this lower power supply voltage is in contradiction with the high voltage swing needed by Lbp Packer. So this is one of the limits of Lbp Packer. On the other hand, LVDS, low voltage differential signaling, has a very good jitter, almost close today to Lbp Packer, although not exactly the same. But the power consumption is less than Lbp Packer, and consequently, it is also available in lower voltages, like power supply voltages, like 1.8 volt, and pretty much popular 2.5 to 3.3 volts. The shortcoming is that the voltage swing is less than Lbp Packer, so the jitter is very good, but not exactly as good as Lbp Packer. So the designer must choose between the two types according to nature of the application. If you have an application that is small and then you need less power, then you try to go to 1.8 volt, it will be Lbp Packer LVDS only. If you have larger applications, larger modules, board level products, and jitter is absolutely critical, then you take Lbp Packer. So these are some of the compromises that are out there.
Well, if I may, Sasha, can I actually ask you about the difference between the Lbp Packer and LVDS? You had said something along the lines of nowadays the LVDS, it's closer in jitter performance to the Lbp Packer. Does that sort of mean that they are comparable in terms of like are LVDS sort of catching up? Is one more prominent than the other? Would you expect LVDS to change, to evolve to be more comparable to the Lbp Packer when you're comparing those two, that trade-off that you were talking about for engineers? Or is that always going to be the two?
Look, there is a race, essentially, there is a race that has to do with bringing to market ICs, because the jitter is the primary limiting element for such an oscillator is the jitter that is generated or not by the IC that is used in the oscillator. So the latest generation of ICs for LVDS are generating jitter levels that are not so far. We are talking about a few percentages away from the Lbp Packer level. But also Lbp Packer ICs are also, improving. So it is a little bit of a race. But we are today, we're working with the semiconductor makers, and we're trying to follow the wish list, the specifications that are imposing. So the concentration is more on LVDS when it comes to smaller applications. And the concentration is more on Lbp Packer when the boards are larger, because you have room to do that.
Perfect. Thank you for tackling that. I believe you are about to dive into more information about the different oscillator types and optical transceivers. Sorry, please carry on.
Yes. So you also have to take a look. So just to continue the conversation about the types of oscillators and the parameters that are involved. We need, so there are, again, as I said in the beginning, we have product, and we're concentrating on product for optical transceivers, which are these type of devices that are shown on this chart, but also boards, modules, larger boards that also are using optical DSPs, and which are used for data center interconnect, metro, long haul applications, etc. And these other boards in general sometimes they use clock oscillators, and sometimes they use VCXO, VCSOs. For the optical transceivers, which are relatively small devices, these have been around for a longer time, in different formats. Since the introduction of coherent transmission protocols, the industry has kind of concentrated on three formats for these optical transceivers. So you have, so these are terminology related to standards of the fiber industry. So you have something called quad small form factor pluggable, QSFP, with different levels of speed. Then octal small form factor pluggable, OSFP, and C form factor pluggable 2, which is the third protocol. And you can see the sizes are a little bit different. QSFP is the smallest, and the industry is going more in this direction. And as the whole industry now is consolidating the designs for 400G, 400 gigabyte per second, and is relatively rapidly transiting toward 800G. This type of modules are becoming prevalent in the market. So the product, the oscillators that we're discussing about for optical transceivers must fit in these sizes, and not only fit, but there are certain thermal constraints and consequently power level constraints that are related to the size of the application and the way it is connected with the rest of the network elements. So essentially, for transceivers, for optical transceivers, these smaller type of applications, the oscillators got to be in a certain frequency, which is dictated by the telecom standards. These are general rules of the industry. There are international bodies that are regulating this, and these frequencies that we're talking, for example, 156.250 megahertz is prevalent for this type of application. So this is dictated by the industry. And there are several parameters which are critical for oscillator that needs to be used in connection with a DSP going into an optical transceiver. So the RMS jitter performance, today what the industry is using right now are levels of jitter under 100 femtoseconds, typical 70, 80 femtoseconds. And the next generation that is already being of DSPs, which is being already considered by many semiconductor players in this market, is trending toward 25 femtoseconds. So that's a preoccupation. We work in that direction. This level of jitter can be achieved today because of advances in semiconductors. So we, as a maker of oscillators, to be very simplistic, such an oscillator is a very small component that has inside an IC, an oscillator IC, and crystal blank. And these two are put together and they form the clock oscillator. So it is critical to utilize an IC that itself can generate the type of jitter, not more than the type of jitter that is imposed by the DSP requirement. Second parameter, which is also very important, is the overall frequency stability of the oscillator, which is today defined at 20 ppm maximum, all parameters included. So what are these parameters? We are talking about temperature stability from -40 to +85 degrees, plus power supply variations, plus shock and vibration, and aging 20 years. So all these variations together must be inside 20 ppm max. And this is, again, it's possible to be achieved today because of, as I said before, ICs of recent construction. And this we combine with oscillators, with crystal blanks, with the crystal resonators that are part of the oscillator, which are of third overtone construction, and which are designed with as flat as possible temperature characteristic curve, so that you can have as little variation as part of those 20 ppm over the temperature range of -40 to +85. And in order to include the aging of the crystal, 20 years aging for a crystal blank is somewhere around 10, 11 ppm. So that has to be reduced somehow. So in some cases, we do pre-aging, accelerated aging on the crystal blanks to achieve that. Thirdly, and remember, this is why I kind of showed the sizes of the optical transceivers, the size of the oscillator must be as small as possible because there is no room in there. And the state of the art today is 2.5 by 2.0 millimeters. So we have in our portfolio clock oscillators, LVDS, as I mentioned before, at 156.250 with jitter under 100 femtoseconds, roughly 80 femtoseconds today, temperature stability 20 ppm, all conditions included, 20 years aging, temperature -40 to +85, and so this size 2.520. And there are several power supply voltages available. So depending on the application, depending on the rest of the circuit, the power supply voltages available in LVDS are 1.8 and then 2.5, 3.3 volts. Whereas in Lbp Packer, they only are available at 2.5 to 3.3 volts. So this is the state of things regarding clock oscillators, which are primarily used in the transceivers, in the small transceivers. Now, if you look at other boards that also are part of the optical telecommunications world, which are larger. There are larger modules in general in the form of daughter boards and larger boards in general. Here, you can achieve better so the frequencies can be 156.250, but they can go up to 1 gigahertz or even more. So we have today designs that go to about 1.5 gigahertz. Remember, now I'm not talking about clock oscillators, but I'm talking about voltage-controlled oscillators with crystal or with SAW device inside, which is the element that is conferring the frequency. And again, the requirements are similar. The jitter must be, in this case, 50 femtoseconds and trending toward 25. And the overall stability, again, can be 20 ppm. Now, the jitter can be achieved much better. A much better jitter performance can be achieved by using voltage control SAW device oscillators, VCSOs. The SAW device, because of its nature, the way it is operating, can operate directly in fundamental mode at high frequency, at frequencies above 500 megahertz and going all the way to 1.5 gigahertz, for example. So we obtain much better jitter than with crystals and clock oscillators by using that. And also we have VCXOs, where we use a resonator at as high frequency as possible with crystal, which is kind of limited at around 212 megahertz. And then we use a multiplication scheme to get to the higher frequency. That for the RMS jitter. Now, for the stability, whereas before, in the case of oscillators, we were talking about 20 ppm, all conditions included, which can be achieved directly with a crystal. In the case of a SAW device, this is not practical because the SAW device is looser in temperature stability. However, this is where, instead of using a fixed clock, we are using a voltage-controlled oscillator with a good APR. This is absolute pulling range. And so the VCSO is part of a PLL, and this is detecting a shift in frequency due to either temperature variations or aging, and the frequency is corrected by the PLL and brought back inside those 20 ppm that the spec requires, the board level spec requires. As far as size, the state-of-the-art for VCSOs and VCXOs is today 5 by 3.2 millimeters. Again, the size of the SAW resonators and the additional components that are needed to achieve such specifications does not allow today, in 2020, to do something a lot smaller. But we are working in that direction. The industry is trying to reduce the size because that's a constant pressure in the world of components. And probably a year, 2 years from now, there will be smaller sizes of VCSOs with such specs. Last but not least, the same level of power supply voltage, 1.8 and 2.5 to 3.3 volts for LVDS, and only 2.5 to 3.3 for Lbp Packer. So these are the comparison, if you want, between fixed clock oscillators, which was this table, and VCXO, VCSO, which I just talked about.
Yeah, this is what I meant in terms of this is the type of slide that you really want to have available on hand when you're trying to measure, weigh your options against one another, when you're trying to understand, when you're looking at all of those different things as you were describing. You've got your temperature stability to consider, you've got your power supply variation, shock and vibration. There are just so many things that an engineer needs to have in mind. And so thank you for laying this out quite neatly. I think that's quite helpful for our audience. I'd like to sort of move us in a direction where we can start talking about actual circuits that we can use these in. So you had talked a lot about, this has sort of been thematic throughout, the idea of it depends on the application, your product, your application, your reference design. Based on your needs, you're going to have several different options available. Can we talk about the circuit configurations that the audience should be aware of, that they have available when they're applying the timing devices? And yeah, it sounds like we've got some specific examples to run through.
Yes. So I think this is quite important. We have launched our product family, the most up-to-date product family of clock oscillators for DSP applications, sometimes at the end of last year. And we have been working with a number of DSP manufacturers to have our specs aligned with theirs. In some cases, we have reached also reference design status. And as the product has been launched in the industry sometime at the end of Q1, some customers have already used the product, and we started to receive questions from engineers about the utilization of such oscillators. And of course, these are in many cases relatively new products, relatively unknown to some of the design community. So we have essentially summarized the type of questions, we have categorized the type of questions that we have received, and we have created an application note to try to respond to these customers who ask questions, and also to have this thing used as a tool for other people, future customers, or people that at some point or another have a practical question about the utilization of such oscillators. So the classes of questions are about four. Okay, there could be more, but essentially this is more or less what we categorize right now. So some questions regard the circuit configuration and are also requesting printed circuit board layout advice. The second category has to do with how to correctly measure the phase noise of such oscillators. Thirdly, concerns about the output waveform, the signal integrity of such oscillators. And last but not least, also very important, questions and issues related to power supply noise rejection. So customers are concerned about noise generated by the power supply available in the circuit in the general application, and how to do that, how to reduce this in connection with the DSP to the oscillators that we are offering. So, yes?
Sasha, may I ask, are these put in order from how popular they are to, how often do you have these types of questions? Is it you get most questions about that PCB layout recommendation, or are there, of the four that you listed, out of curiosity, what do you see the most?
To be honest, I think we see a little bit of each. It's not one that is prevalent. It depends. You know, we have been in dialogue with several customers, and some had questions about 2 points out of these four. Some had only one. So you know, but without getting into very deep details, because that's a very technical conversation, I encourage the audience and other further customers to make reference to the application note that we have put together. It is attached to our virtual booth in this All About Circuits show. And also it is part of the Oscillators for Optical Transceiver section of our website. We also are available for technical conversations, detailed technical conversations about that with our applications engineering team. But just to very briefly tell you what these are about. So regarding the circuit configuration and the PCB layout, we are making recommendations. So here you have a schematic, a typical schematic that we put forward. Here you have the oscillator. There are a number of elements which can be bypass capacitors, ferrite choke, and in some cases we recommend the use of LDO, low dropout voltage regulator. And then you have the load. So it is very critical that the outputs of an LVDS oscillator be matched in impedance with the load. So it is critical to have the traces at 50 ohms and the input of the DSP, if it has 100 ohms load inside, okay, that has to be recognized, and if there is not inside, then it has to be put outside. So these are, you know, some circuit details that are covered in the application note, and we welcome any kind of inquiries about that. Second, we had customers who made observations about the phase noise, that they could not achieve the same phase noise measurement results as our stated results on our specifications. And every time when we started such a conversation, in general, it turned about what kind of circuit is being used for making the phase noise measurement. Again, this type of LVDS circuitry must be balanced, and the impedance must be correctly matched on the output. If not, the results are not correct. And so we also recommend the usage of the phase noise analyzer power supply as a power supply voltage source for the oscillator when a phase noise measurement is made. Because this type of instrument has a very clean power supply, and then you will not inject any kind of unwanted noises when you make such a phase noise measurement. Again, that is in the app note. Thirdly, we are talking about the output signal integrity. People have sometimes measured, they did not get the perfect eye diagram for an LVDS oscillator. There were ringing, overshots. So it is very important here to use as clean as possible a power supply when you take the output waveforms. The use of matched impedance coax cables is very critical when you take the output waveform. And likewise, when you do such a test, you need to measure this eye diagram, the output levels, and the waveform, the rise and the fall time, and the waveform symmetry. These are the points that need to be measured. Last but not least, very important, it is important for the customer to use as clean as possible a power supply in the application. Sometimes this is there inherently, sometimes it is not the case. And we are recommending several circuit configurations. So here we're talking about a little bit of a balancing act between optimum power supply noise rejection and the size of the circuit. So in particular for, as I said earlier, a small transceiver, the number of components and the size of components used next to the oscillator is critical. So we have, there are 3 types of circuits that we have recommended depending on what is practically there in the customer's application. So every customer has a little bit of a different situation. So there are 3 circuits, one that is using only bypass capacitors. It's not all here on this schematic. You really need to look at I did not put so much information here because I thought it would become too complicated, but it's all in the app note. And we recommend 3 circuits, one that is using only bypass capacitors, one that is using bypass capacitors and a ferrite choke, and a third one that is also using a LDO, low dropout voltage regulator. And we compare the phase noise, the jitter in those 3 cases. And we, of course, find that the circuit using the LDO is the best from a power supply noise rejection point of view. Now, we have spent a lot of time studying the market for finding an LDO that is very small in size. So if the customer's circuit is such that when using the oscillator, there's too much noise, then we recommend the use of such an LDO. And we are ready to discuss with the customer. Maybe we can take it offline if somebody wants to come to us through the chat on the virtual web or virtual exhibition, or directly to us later. We welcome such conversations.
Great. Yeah, that's a good segue, actually. I was going to mention, as we get towards the Q&A here, the white paper that Sasha referred to is on the virtual booth, allaboutcircuits.com/tech days/summer2020/Raltron. You'll be able to find it. If I'm looking at the right one, Sasha, you can correct me if I'm wrong, but it's under the title of Ultra Low Jitter High Frequency LVDS Clock Oscillators. And you'll be able to see that right on the page.
Yeah, that is correct. The application note, I think there is a section called App Notes where you can find this.
Yeah, perfect. So everyone, a lot of what Sasha's been talking about here, that's available on the booth page. Go check that out. Also, I'm going to remind everybody as we transition into this Q&A session, there's that widget down at the bottom of your screen. If you have a question for the president of Raltron, not every day you're going to get this opportunity, so I'm going to recommend that you hop on it. We do have one last order of business before we get to the questions that we already have, and that is to announce the winner of the giveaway package today. So congratulations to Bruce Scoggin. Bruce, our team will track you down and we'll get your t-shirt size and we'll get you hooked up with your prize package as soon as possible. Congratulations, Bruce. So with that out of the way, let's get to some of these questions that have come in. Sasha, are your oscillators mentioned on any reference designs of DSP manufacturers?
Yes, they are. We are working with several DSP, optical DSP manufacturers. And although, we cannot mention all these names openly here for obvious NDA reasons, there are not so many DSP, optical DSP manufacturers out there, but yes, we are today on at least 2 of them on their reference designs. And
awesome.
Yes.
Great, thank you for tackling that. Next one that's come up is, do you accept application-specific requests for development?
Yes, and as I mentioned earlier, we have 2 applications engineering teams, one here in Miami where we are headquartered, and another one in our Shenzhen operation. These applications engineering team are staffed with people who are, very capable and have a lot of years of experience with such oscillators and designs. We encourage questions from customers and potential customers. And one of the things that we are offering free of charge is circuit analysis for our customers. So we encourage this to happen as much as possible at the beginning of a new design. This is when we can make the most impact, where we can use our knowledge and expertise to explain to the customer what are the compromises between various parameters and also direct the customer toward selection of the optimum configuration, circuit configuration, and component values. But we do that also later. Sometimes the customer has already an existing application and they are not perfectly happy with the performance. And we dialogue, and then we get the boards, we make measurements, we take test data, and we discuss with the customer. And again, we make recommendations for component values or circuit configuration adjustments.
And yeah, that's another sort of theme that we hear across Industry Tech Days as well, is the sort of plea from experts such as Sasha and Raltron in general to reach out, ask for help, get in contact, involve your partners as early as you can in the design process. So it's good to hear that echoed here as well. The next question is, are all frequency products available through distribution?
Yes. The majority of the frequency components in our portfolio, at least the combinations of packet size and frequency and the key parameters, temperature stability, and for crystals, equivalent series resistance, etc., are available through distribution. We are engaged strongly today with DigiKey, where most of our products now are available for immediate purchase. There is inventory there, including these optical DSP related oscillators. We also have relationships with other distributors, Future, Richardson, RFPD, RS Components. We are in the Element 14 catalog, some regional distributors as well, DAV, which is a frequency components distributor in North America, and a number of regional distributors in Europe, in Japan, in Israel, and in Asia.
Okay, thank you so much. This is a pretty good one. What trends are you seeing for the next generation of oscillators for optical DSP applications?
Okay, so I kind of hinted a little bit in my previous statements toward such trends, but if I had to put them all together in a statement, what we see is obviously the frequencies are always going higher. That is linked to the constant pressure to put more debit through the existing pipelines. And what is today 156.25 frequency for DSP-related clock oscillators probably will trend to double that much. So we already are working in the direction of 312.5 megahertz. That is a little bit of a challenge because it cannot be achieved with crystal only. There are some additional circuitry that needs to be added to get to that frequency when you use a crystal blank inside. But we are working in that direction. I have mentioned the jitter requirement, which is pretty much today the next generation of DSPs, which is not on the market, but which will be on the market maybe in a year from now, is asking for 25 femtoseconds jitter. So that is not easy, but obviously ourselves and sure other people who are in the same branch of clock oscillators, we're working in that direction. Last but not least, the power supply requirement that is also linked to power. It is challenging. It's difficult to get LDPC to 1.8 volts, but I'm sure that the semiconductor industry, people that we are buying from, the IC that goes into our oscillators, is working in that direction. And last but not least, also very important, as I mentioned before, the current smallest size clock oscillator for optical DSP applications is 2.5 by 2.0 millimeters. the next smaller size, standard smaller size of the industry is 2 by 1.6 millimeter, 2.0 by 1.6 millimeters. And that probably will be the next target for size. So these are pretty much the important parameters that will change with time.
Awesome. Really like that breakdown. And I think we have time for one more question before we wrap up today. And it kind of segues nicely with what this last question was. So given the trends that you just laid out, that the higher frequencies, the changing jitter requirements, smaller sizes, what is the roadmap for Raltron moving forward? What's next?
Well, for digital signal processor related oscillators, I think what I just said is the roadmap, at least for the next year or two. As a company, obviously not related to this particular subject, but we will continue to put a lot of emphasis on precision oscillators, OCXOs, Stratum 3 TCXOs for the 5G, this miraculous 5G that everybody is talking about, on one hand, and the very strong increase in IoT-related applications, where we have not only crystals, but also filters, SAW filters, ceramic, low-temperature confined ceramic components, and in particular antennas. That is a very fast growth segment for us, and we will put a lot of emphasis there as well.
Mm-hmm. Well, I think we're at the end of our time for today. So let me just say one more time, go check out the Raltron booth. There's that awesome white paper, app note rather, that Sasha's been referring to on and off here, the ultra low jitter, high frequency LVDS clock oscillators. If we didn't get to your question today, or you think of one later, or if you're listening to this on demand and you want to submit a question, don't forget the live chat function on the Raltron booth as well. Let me thank everybody for taking time out of your day to be here today. And also, huge thanks to you, Sasha. This has been extremely helpful.
Okay, thank you. Thank you very much for having me. And I appreciate also the opportunity to talk to the engineering community. And beyond the show, which we find very interesting, profitable, it's the first time that we engage in such a virtual show. Thank you, All About Components, for that. When the show is over, you can continue to, for a certain amount of time, to look at the materials that will be displayed there. And later on, we invite you to visit our website and contact us directly in Miami or in our Asian offices. Thank you very much.
Well, thank you guys, everyone, for a really great live session. And I hope that you enjoy the rest of day 4 of Industry Tech Days 2020. Thank you and have a good day.
Thank you. Okay. Bye-bye.